Hello and welcome to another video from HPart. Today we will be modeling two basic flashlight designs, one based around a lens and the other based around a mirror. In the video today we will be using fresnel, which is free optical design software available at h-part.com. Alright, let's get started. So the key to any modern flashlight is the LED. And in these designs, I'm going to be using the Luminos SST-40. It's a pretty common LED for these kind of things, high power, bright light, and it's of course a white LED. Now to model an LED in Fresnel, we really care about two things. We care about the wavelength distribution, which is on this page of the datasheet for the LED, and we also care about the radiation characteristics, which is the radiated power per angle relative to the normal vector of the LED. Now, to import this into Fresnel, we have to get this data into a CSV file or two CSV files with the right headers. Now, if we can just go ahead and create our emitter, which is going to be a point source emitter. We're going to put it at the origin, and we're going to create an emission, which will be a point source emission. We're going to select non-uniform for our wavelength distribution, and we're also going to select a custom symmetric intensity distribution. Now you see these two upload icons? This is going to tell us the CSV headers that we need. We need one with wavelength nm and weight, and the other one is going to be theta degree and weight. Now I won't go through creating these CSVs, but I will note that a very fast way to do it from a datasheet like this is actually to export just this page of the datasheet and put it into Gemini or your favorite AI chatbot and tell it to generate the CSVs with the desired headers and then manually check it. It tends to do a pretty good job, at least Gemini does. Anyways, either way, once you have the two CSV files, you can go ahead and upload them. So you click on the CSV upload button, and you pick the, let's see, wavelength CSV file. Go ahead and upload that. You can see we've got our wavelength and our relative wavelength distribution. We can see the two peaks here, one at 550, one at 455. These are the same peaks that are shown in the datasheet for the 500K path. Then, or sorry, 5000 Kelvin color temperature. Then we're going to do the same thing down here for the intensity distribution, which would be the angle CSV. And it's going to update our angles. And we can see that it's strongest at an angle of 0 degrees relative to the normal of the LED. And it drops down to 0 at 90 degrees. So that looks about right. And now I'm going to scroll down here, and I'm actually going to render the intensity surface. This is a useful diagnostic tool to allow you to see if you've entered something relatively correctly. So we're expecting a kind of hot air balloon shape that goes down the z-axis. So let's go ahead and cast that. And zoom out a bit. All right, and we're going to just reset the bounds here. Perfect. So now what can we see? Well, this orange shape here represents the intensity based on the angle from the normal of our LED, which is represented by this point source right here. Now if we zoom in here and take a quick look at these rays, we can see how these rays here line up with the tangent of this cone, which kind of comes right down to here, right about 90 degrees. And there are a lot more rays in the middle of this cone than there are towards the edges. These are the fainter rays, and so that's how the intensity, I guess, hot air balloon lines up with the individual rays. This can be useful if you have a more complicated intensity function that might have, say, multiple lobes, because it allows you to visualize the lobes and thus know that you've gotten the intensity in correctly. So now that we've seen that and seen how it lines up, I'm going to go ahead and get rid of it so it's no longer distracting us. And here we have our LED spitting out, what was it, about 1,000 rays. Yep. All right, good. So now that we have the LED modeled in Fresnel, we need to move on and actually add a lens that is going to collimate or at least guide the light to form our flashlight. Now for this design, our goal is not to make a narrow beam, high throw kind of flashlight. It's actually going to make a wide beam flashlight. And understand kind of what we're starting from. We're going to go ahead and add a detector. We're going to make it pretty big, and we're going to make it approximately, we'll put it out maybe at, say, 100. See how that looks. I'm going to rotate it 180 degrees so it's looking down the negative z-axis towards our LED. Okay, so here's our detector, here's our LED, and of course we're going to add a detection. We're not going to put any gates on it right now, and we're just going to go ahead and recast. And so we can see that we've got a lot of light hitting this detector, but an even larger, or well, not a larger amount of light, but a substantial angular piece here is actually missing the detector entirely. It's worth noting that that's not a large amount of the intensity of the LED, but I am kind of curious. So I'm just going to go ahead and create a collection efficiency analysis, and I'm just going to capture all detector hits. I'm going to go ahead and run that. So we can see that about half of the light is actually hitting our detector. Now this would be a very wide angle flashlight. Now I'm kind of curious about how the intensity of the light is going to fall off as we move towards the edge of the detector. So I'm going to go ahead and create a relative illumination analysis. I'm not going to filter the stray rays. I want all the detector hits. Now I'm going to go ahead and run that analysis. So this is what I see. You know, we're pretty good in terms of illumination right here. And then once we get out about halfway through the detector, it starts to fall off. So this is going to be a smoothly varying intensity plot if we were to, say, shine this at a wall. We aren't going to see any rings or cones or strange artifacts. Now let's go ahead and put in a lens. I'm going to zoom back in a little bit for it. We're going to go with a 25mm diameter lens. It's going to be just a simple PCX lens. I'm going to go ahead and, let's see, I'm going to try a, yep, so I'm going to go ahead and increase the center thickness just to give us a little bit of play. Because our goal with this flashlight, maybe that's a little bit too much. Okay, so our goal with this flashlight is going to be to get most of the light in a 10-degree cone. So this is going to be not a narrow beam flashlight, but not a very broad beam like we currently have, where it's just throwing the light everywhere, so it'd be difficult to see anything. We're going to compromise. We're going to throw out the beam at about a 10-degree spread, and we're going to optimize the lens to do that. So I'm just going to kind of get us in the ballpark. That's probably, it might be a little too steep. Let's see what the minimum radius would be about that. So I'm going to increase my center thickness to support it. That would be about 12.5. Okay, there we go. So now I've got my lens. NBK7 is fine. You could do this in plastic if you wanted to. Some flashlights have plastic lenses. We're going to put this, I don't know, maybe 15 millimeters in front of the actual LED itself. There we go. So now we've got our LED source, we've got our revolution, we've got our detector, which is playing the part of our wall. And as we go through this, we're first going to optimize for 10 degrees. Then we're going to assume that we have a variable zoom flashlight, and we're going to assume that we're actually going to move the lens out. I'm going to show you how to understand what's going to happen to your beam of light as you move the lens. But first, let's just see if we can get our 10 degrees. So I'm going to go ahead and recast the light here. And you notice we get a kind of immediate total mess. The first thing we can see is we've got a lot of light that's going out this way, and we've got also just a substantial amount of stray light that's making this hard to see. First thing I'm going to do is drop the opacity here, and I'm also going to add a light path just so we aren't distracted by all these stray rays. I'm not going to use the light path in the analyses because we actually are very interested with a flashlight in the stray light because the user is going to see it. So the light path here is just more for our own I guess, diagnostic clarity. So I'm going to go ahead and grab the back surface here, and then I'm going to grab the front surface. I'm also going to go ahead and grab the detector, and I'm going to drag that light path up top. I'm going to assign it to our point source, light path, and I'm going to cast it. Good. And then I'm going to hide the stray rays. Okay. So here's what I'm seeing. Now I'm going to take a look at this collection efficiency. We were about 40%. Now we're up at about 62%, so we're getting more light. But if I filter the stray rays and run it again, you see we're down at 23%. Now this is not ideal because we want most of the light to go through the lens and thus achieve the desired angular spread that we're going for in our design. A next question could be, what exactly is the angular spread that we're currently getting? Let's go ahead and create an angular spread analysis. We're going to go ahead and filter the stray rays. And I'm interested in the median angular spread. Go ahead and run that. As we can see, our median's at about 5 degrees. And we want to increase that to about 10. So now we need to optimize our lens, both to improve the collection efficiency of the light that's actually going through it, and to improve the angular spread to get it to that desired 10 degrees. We're going to create a merit function for that. And our target's going to be our collection efficiency and also the angular spread. Now, we're actually going to filter on stray rays for both these analyses. Yep, good, because we want to make sure that the light is actually going through the lens with the collection efficiency. And then angular spread, filter stray rays, great. We care about the light that we were getting. Okay, very good. So now as far as targets, for a flashlight with a single lens, maybe 70% collection efficiency would be a good target. We're going to penalize below. Angular spread, we want both sides of the target. We're going for a target of 10 degrees and a threshold of maybe 9.5, so within half a degree, that'll be good enough. We want to be able to optimize where the lens is and also the lens's radius of curvature. So I'm going to go with Z millimeter for where the lens is, and then the radius of curvature will be that. All right, now as far as where the lens is, down to that seems like actually a pretty good range. We might actually want to allow it to get a little bit closer. But that's about as much as we'd like, just to give us clearance. 25 is fine. Then we're going to limit this one as well. Now we can't get any smaller with a 25 millimeter diameter lens than 12.5 in the radius of curvature, so we're actually going to leave that as the minimum. And for a maximum, we'll just dial it up to 30. And so we've gone ahead, we've created our merit function. Let's go ahead and calculate it, see what we're doing. So most of our issue here is currently in the angular spread department because we're so far off. Let's see. Our next step is going to be to create an optimizer. We'll stick with CMAES. We're going to use our merit function. We're going to go with sequential optimizer because we have a light path active. 5,000 evaluations would be fine. 500 we could probably get away with. I'm going to go ahead and create the optimizer. Now I'm going to move this over to the right a bit so we can see it while the optimizer is running, and then start the optimizer. All right, and we're done. That didn't take very long. We were basically finished around 200 evaluations. We can see there are a lot more rays that are showing up as non-stray. We appear to have increased the radius of curvature ever so slightly, but the biggest change is that we actually moved the Z position closer towards the LED a bit, from our original 15 millimeters down to about 12.5 millimeters. All right. So now let's take a look at the merit function and see how we're actually doing in terms of the collection efficiency we wanted to hit and the angular spread. So taking a look here, we're basically right on the money in terms of a 10-degree angular spread of our beam for our flashlight, and our collection efficiency is actually right around 70%, which is what I guessed would be the case. We're within range on our optimization variables. And so this design is looking good. Now I'd like to actually open up the display and take a look at the stray rays just to see how we're looking overall. I'm going to open this up and I'm going to uncheck hide stray rays. And I'm going to, I think I'll drop the opacity a bit more. And so we can see that we still have a lot of stray radiation that's going backwards into the flashlight body. This is bouncing off the inside of the lens. It's also just reflecting off of the side of the lens. But we notice that most of the light that is going forward and making it to the wall itself is actually passing through the lens. And that's good because that's what our collection efficiency was telling us in the analysis and in our merit function. Roughly speaking, because we're filtering stray rays, about 70% of the light that's emitted by the LED is actually passing through the lens, being properly refracted, and hitting the surface. Now let's take a look at the relative illumination. Now we don't want to actually filter stray rays here because we're interested in seeing what the pattern of light looks like as we proceed away from the center of our detector, center of our wall. So let's go ahead and run this. Now what we see here is fairly flat intensity, and then a peak towards the edge, followed by a rapid drop, and then very, very little light outside of this initial cone. Now, this raises an immediate question. Why is it so flat here, and what's causing this peak? The first thing we can do to investigate this is we can actually filter the stray rays and see if the peak is being caused by a bunch of, say, stray rays hitting at that spot. We're going to save this and rerun the analysis. And when we pull out the stray rays, we find that it actually looks worse, and the peak is still there. So the stray rays were effectively just smoothing around the peak. But we still have this peak out at about 0.275 on the normalized radius for the detector. The question is, where is this peak coming from? And to answer that, we're going to look at the light edge on, and we're also going to go ahead and enable section view. So I'm going to open up the display, and I'm going to turn on section view, and then I'm going to scroll down here, and I'm going to do a couple things. First, I increase the opacity so we can really see the rays, and I'm going to start to widen the section view so we can capture more rays. So watch carefully as I widen this section view. Okay, I'm going to start to pull it out, and we're going to see more rays traveling through the system. And if we pay attention, we can see what's creating this peak. I'm going to pull it back. Did you see it? Okay. So now we're right about where our original section view is. And what you notice is we have the light that is coming out, let's say on a quote-unquote normal trajectory, is going through the lens, and it's heading somewhere around here, somewhere in this area where our peak is. And this looks like, just based on these rays, there shouldn't be a peak, because there's nothing here that's creating, say, a bunch of different rays from different angles out of the LED to hit in one spot, and that's about the only thing that would create a peak. However, I do notice something interesting. This green ray right here, and I'm going to pull the opacity all the way up so you can see it. This green ray right here is actually traveling down. So this is actually going to intersect with the rays that were coming through more of a regular path through here. And that means there's going to be intensity that's up in the top of this lens that's going to hit in this area. And that is what causes the peak. Now if you watch carefully as I drag this slider out and pull the opacity back down, you're going to notice that there's more and more of this light that is traveling through this part of the lens and actually intersecting down here. So right in this area is where a lot of this light is hitting. As we can drag this out, we're going to see more and more light is actually traveling this way. It's creating this view here, and then it's hitting right around there. And the fact that basically two angular ranges, this angular range here and then this angular range here, which are both large amounts of area of the lens because they're out near the diameter, both of these areas are actually hitting and intersecting in the same place over here. And that's why we get our peak, which we see right here. And when we allow the stray rays, it turns out that it smooths that out, a little bit of the noise effect. But to make a long story short, the peak that we see in the relative intensity here is due to the fact that there are multiple angles of emission from our LED that actually wind up in the same place. So if we were to shine our flashlight at a wall, we would actually notice that there would be a bright ring created by this effect. All right, at this point, we have created a flashlight that has a 10-degree angular spread, and we've analyzed its relative intensity. We've also understood why the relative intensity curve has the shape that it has. And finally, we're getting a pretty good collection efficiency of about 70%. Now, if we just wanted a fixed lens flashlight, perhaps this would be good enough. But some flashlights actually have a zoom lens, where the lens can be moved out farther away from the LED to tighten the beam. Now, if we wanted to add this feature to our flashlight, a natural question to ask would be, how far should we allow the lens to move out away from the LED to get the desired amount of change in our beam? And how much are we willing to pay for that in terms of a drop in overall collection efficiency? So to better understand that, we're going to close these relative illumination analyses, and we're going to open up a scanner. And a scanner will just allow you to move the lens farther out and record and plot certain metrics that are of interest to you. So what we're going to do is we're going to select the revolution position Z. We're going to start at its current position, which, let's see where the optimizer put it. Okay, it was that, oops. I'm actually going to close that since I accidentally cleared it. Edit that, okay, so now it's back up. I'm going to close that. I'm actually going to place that in as our minimum. So we're going to start at where we want our base setting for our light to be, which is 10 degrees. And our maximum is going to be, I don't know, let's suppose we wanted maybe a 1-inch travel on our lens. So adding about 25 millimeters to our initial 12 puts us out at about 37. So we're just going to round up to 40. We'll do, say, 50 steps, so it's a super smooth curve. And we're interested in the angular spread, so how that changes. And we are also interested in the collection efficiency of the lens. So now that we've defined what we want to change, what range we want to change it over, and the outputs that we want to see, we're going to go ahead and create that scanner. And now we're going to run the scanner. It'll take a little bit, and here we go. So now what we see are, I would say, 3 distinct regimes. The first here is the angular spread is positive. Then it goes negative, and then it suddenly shoots back up to positive again. And all the while, the collection efficiency falls down to about, maybe 6% when we've gotten all the way out to 40 millimeters on our Z position. Now, you might be asking, why does it go negative and why does it go positive again? Well, to understand that, you first have to understand what the sign of the angular spread analysis means. A positive angular spread value means that the rays of light are diverging at the detector. And a negative value means that they are converging. So after a certain point, as we move this out, the light is no longer diverging. It's actually converging. And right about this point, the light is collimated. And at some point, the light starts to actually cross in front of the detector and it becomes diverging again as the efficiency slowly drops. You'll also notice that the noise goes up as we get farther and farther out here. And the reason for that is that there are fewer and fewer rays of light that are actually being included in the analysis as the collection efficiency falls. And that just increases the noise and decreases the smoothness. Now, just to make it concrete, I'll show you a picture of each of these 3 different regimes. The first one we actually already see on the left. That's our 10 degrees of angular spread, and we have a nice diverging beam. Then I'm going to actually go ahead and put us over here around 20.4, which is where the beam is collimated. Go ahead and move the Z out here to 20.4. Okay, and I'm going to recast this light. As we can see, we're pretty close. I may have missed just a little bit, but we have a roughly parallel beam here. I'm going to go ahead and run the angular spread analysis. And so most of the rays of light, and I know the envelope makes it look a little bit more convergent than it actually is, but most of the rays of light are nearly parallel to the normal of the detector. Then, say, right around a Z of 25 or 24.3, we're actually starting to strongly converge. Let's go ahead and move that a little bit farther out to 24.3. So we've gone out a little bit more. And now we're going to recast the light. And we can see this is a very convergent beam. And we're actually kind of more or less focusing the light to a point, which is rarely what you want to do with a flashlight. And then finally, out at about a Z of 30, we've actually crossed ahead of the detector and we're starting to diverge again. Let's go ahead and save that, recast, and you can see that a lot of the light here is actually crossing in this region and is diverging. And if you take a look at the relative or at the angular spread analysis, you're going to see here that we still have a fair amount of convergent light, and that's this central cone in here, but a whole bunch of the light is actually divergent. Some of it is, like this ray here, is wildly divergent. Now, what implications does this have for flashlight design? Well, if you wanted to design a zoom lens on a flashlight, you definitely don't want to get into this regime here, where you've got a divergent beam that's crossing over in front of the target. And you probably don't even want to have this regime here. You likely want to stop your Z travel right around here where the beam becomes collimated. So, given that our base case is about 12.5 millimeters, I would design the flashlight to allow the lens to advance only up to about a Z value of about 20.4, maybe 21 millimeters. That's where the beam comes collimated, and a little bit farther it will start to converge again. So this completes the portion of the video where I'm going to talk about the design of simple flashlights using lenses. In the next section of the video, we are going to move on to talking about flashlights that use parabolic mirrors to produce a very focused beam of light that can travel a long distance and maintain its collimation. To that end, I've gone ahead and duplicated our flashlight lens design using the duplicate button up here, and I've deleted everything except the emitter, emission, detector, and detection. Essentially, that just leaves us with the LED that we had and a wall. So I'm going to go ahead and cast the light from this LED, and we can see that it's producing a nice diffuse illumination of our detector. Now, our goal in this design is to create a parabolic mirror that's going to launch a collimated beam of light that we could throw over long distances to illuminate the target. So we need to go ahead and create that parabolic mirror. To do that, we click on Quadric Surface. This opens up the Quadric Surface Create panel. The default quadric surface is conveniently a parabola, and it has two different inputs, the aperture radius and the focal length. We're going to start with the aperture radius because that's going to be fixed throughout the duration of this design. The aperture radius defines the radius of this circular lip of the parabola. And since we use 25 millimeter diameter lenses, we're going to go for a 12.5 millimeter radius for our parabola. Now, the next thing we need to set is the focal length. This determines the shape of the parabola. A very large focal length will give a very flat parabola, whereas a very small focal length will give a very narrow and steep parabola. Now, it should be apparent that if the LED is sitting back here and it's launching light out like this, the steeper the parabola, the more light it's going to capture. Another way of looking at that is a very flat parabola is going to miss nearly all of the light that the LED produces. So we want something steep, but not too steep that it's difficult to manufacture. So we're going to start with 3 millimeters. That gives us a nice and convenient shape. And we're going to put the parabola offset by -3 millimeters, the same amount, so that the focal point of the parabola is coincident with the position of our LED. Go ahead and create that, and we can see it right here. And now let's go ahead and let's recast the light. Now what we notice is, effectively nothing happened. We did not get our main beam of light that we can illuminate targets at a distance with. The light just went right through the parabola. And this is because we've only created a parabolic surface. We haven't created a parabolic mirror. To do that, we need to go ahead and apply a coating to our quadric body. I'm going to head and open the coatings panel. I'm going to pick Perfect Metallic Reflector. And I'm going to save that. Now before I recast the light, I just want to take a brief pause and talk about the coatings panel. If you had wanted to create your own custom reflective coating with maybe a different behavior than the Perfect Metallic Reflector here, which is 100% reflectance, overall wavelengths, you could open up the New Coding panel, and you could create angle of incidence tables for different angles of incidence, and the software would interpolate between them. For each angle of incidence, you'd want to create a reflectance curve, which would be previewed below. And you could also do that by uploading a CSV file. But for now, in this design, a perfect metallic reflector is good enough. So we'll stick with that. Now let's go ahead and recast the light. Okay. So now we have our main beam that was going to go out and illuminate the target, and then we have the diffuse radiation that's coming straight out of the LED and missing our reflector. Now if we look at this, it looks from my perspective like the light is actually slightly converging, but it turns out that this is an optical illusion created by the diffuse radiation passing through this collimated beam. To see that, I'm going to pick one of the rays that's in the main beam. I'm going to use the ray picking tool. I'm going to zoom in here. I'm going to go ahead and grab this ray right here. Now it's a little bit faint, so I'm going to drag the opacity all the way up and move back out here. So this is our ray of light. It's traveling from our LED, hitting our mirror surface, and then moving towards our detector. And if we look at the path of this ray, we'll notice that the x and y coordinates it has at the point of reflection are the same exact x and y coordinates it has when it hits the detector. And this means that our ray of light is perfectly parallel to the optical axis. Alright, now I'm going to go and reset this back to the low opacity we had before. I'd also like to note one other thing. The axes for the local coordinates, x and y, for our parabola, which is in blue, have been drawn. And also the focal point, this orange dot, has been rendered as well. This can be helpful for visualizing the curve that's creating this surface via a revolution. All right, now we have our main beam of light, and we have this diffuse beam of light, and we could be done right now. But let's push this a little bit further and ask what, if anything, we can optimize in this design. The first thing to note is our goal here was not to produce this diffuse radiation that misses our parabolic mirror. Our goal is to get everything we can into the beam. So to start, I'm just going to look at our overall collection efficiency, and I'm also going to consider the collection efficiency of just the light that's in the beam. So I'm going to create two analyses to measure that. So first will just be a collection efficiency for all of the rays, and we're going to go ahead and run that. And that shows us both our central beam, which appears to be more of a donut shape, and then the diffuse radiation that's hitting outside of that. And we note that we're getting about 79% of the light onto the detector. Now I want to create a new collection efficiency analysis that uses a light path to just focus on these rays. So go ahead and create that light path, which will be very simple. Just grab these two surfaces. We got that done. I'm going to go ahead and assign it to our point source. And here we go. And I'm going to create a new collection efficiency analysis that will filter the stray rays. I'm going to rerun that. And here we're just seeing the rays that have actually hit our mirror. And we notice that while our initial collection efficiency was quite high, this is just 32%. And we can also clearly see the donut shape. I guess I'll take a brief pause and explain why this donut shape is occurring. Again, if we zoom in here, we notice that for the light to actually hit the mirror and travel to the detector in the main beam, it has to first travel out before it can hit the mirror. And it's the traveling out that creates this dead space in the middle of the donut. Any ray of light that does not travel out is very unlikely to be parallel to the optical axis and thus hit inside this donut, especially at long distances. So this is why we see the effect that we have here. Now it'd be nice to get this up higher than 32%. And as I mentioned earlier, we really only have one knob to turn, which is the focal length of this parabola. Let's go ahead and open this back up. So we can see here that if we increase this, it gets flatter, which is the opposite of what we want to do. If we decrease it, it gets narrower, maybe more difficult to manufacture, maybe not, depending on our application. So I'm going to go ahead and create a scanner so that we can better explore how the collection efficiency is going to vary with the focal length of the parabola. Now to do that, I need to make it so the parabola automatically scoots backwards as I change the focal length so that we can always keep the LED in focus. Now for that, I'm going to create a formula. And the formula is going to be I'm going to call it parabola Z. And that's going to be based off of the focal length of the parabola, which I'm going to call FL. And the parabola Z is simply just going to be negative FL. So now I've created my parabola Z formula. I'm going to open up the quadratic body, and I'm going to put that in place of the hard-coded Z coordinate. So now, as I vary the focal length of the parabola, like so, maybe 5, it will automatically scoot back and keep the LED in focus. Now the next thing I'm going to do is I'm going to create a scanner. Now we're going to scan over the focal length of the parabola. So I'm going to go ahead and select that. And we're going to go all the way down to a minimum of 1, which may not be physically manufacturable, and up to a maximum of 10. We'll do it in 100 steps so that it's smooth. And we're going to care about the overall collection efficiency, which is collection efficiency 1, and then the main beam collection efficiency, which will be collection efficiency 2. So I'm going to go ahead and create that scanner, and I'm going to run it. It'll take a little bit, and here we go. So what we see is that the collection efficiency rises rapidly within the 3 to 2 millimeter range, and it maintains a roughly constant gap against the overall collection efficiency, which peaks at about 100% at a value of 2 and gets matched at about a value of 1. So what can we glean from this in terms of actually designing our flashlight? Well, it seems that the shorter the focal length, the narrower the parabola we can make, the better we do. And I believe we started with a value of around 3, which landed us here at roughly 80% overall collection efficiency, but only 32% in the main beam. So it might be possible that we could get the focal length down to maybe 2 millimeters. And that would give us a collection efficiency of about 62%, and we'd actually be getting all of the other light would be hitting our detector. That's a bit of a misnomer, just because our detector is so close to the light. If we move the detector farther out as like a wall, that would change. But 62% seems reasonable, so I'm going to go ahead and actually decrease the focal length down to 2. I'm going to take a look at it. So here we go. Now let's go ahead and cast the light, get a nice narrow beam, recompute our collection efficiency, 62%. We got our nice clean donut here. We understand why it's a donut. The donut's gotten a little bit narrower because the bottom of our parabola has come closer to our LED. And now the only thing that would be left to consider is whether this is manufacturable, whether maybe we're going to cut off the bottom of this when we mount it onto the PCB where the LED is. These are the kind of questions that we would have to answer. But for now, I'm satisfied with this design. We've accomplished our objective of throwing a bright beam of light that includes most of the light from the LED and would be capable of traveling a large distance. Now in a simulation like this, the beam of light will travel infinitely far, but in practice, the parabola won't be perfect, the LED won't be perfectly in the focal length, the focal point of the parabola. The LED has a physical dimension, which means that some of the light is actually going to be coming from different parts of it rather than a point source as we've modeled it here. And all of those factors are going to cause the beam of light to begin to diverge. Nevertheless, this is great for a rough approximation and gives us a good understanding of the principles at play when it comes to designing a mirror-based flashlight. So to sum up, we started this video with some lens-based designs, then we moved on to some mirror-based designs, and in each case we discussed how to optimize the design and understand how it functioned. And that's all for this video. Thank you very much for watching, and I'll see you next time.